In this lecture, we are going to build up the derivative of the two variable or multivariable functions. First, we are going to define limit. If f is a function of two variables whose domain D includes points arbitrarily close to AB. AB is a point in its domain. And we say that the limit of f as xy, the pair of variables, approaches AB is L if you have a small ball around AB. So here's your AB in the domain. And you can find the little ball around AB such that this whole ball is mapped by your f into like a small range small interval near the limit. Okay, and no matter how small you want your interval around L to be, so you say, I don't want that much, I only want this much around L. You go back, look at the ball around AB, you can find a smaller ball that make it happen. So the whole ball around AB, centered at AB, okay, is mapped into this, all the values go into this small interval around L. So you come up with a small L, I can find you a smaller ball. That is the idea. Go back to the wording of the definition. If f is a function of two variables whose domain D includes the point AB and also the points arbitrarily close to AB, which means a little ball around AB. In dimension 2, I should call it a disk. Yeah. Then we say that the limit of f as xy, again the pair of points, approaches AB is L, and we write it as the pair of variable approaches to the point xy goes to AB of xy equals L, the sort of the terminal value. If for every number epsilon greater than 0, this is the epsilon I'm talking about, around L, you can find the corresponding number delta, that is the radius we are talking about on this side, such that if xy sits in the D and xy not only sits in D but also it sits in this little ball, then when you map it under f, it will fall in this little interval. Okay, so that's the idea. We are not going to do the precise epsilon delta kind of definition or the proof, so we will have to have another way of confirming functions has limits, or have a way to know that functions don't have a limit. Okay, so let me take away my drawing and continue. Okay, so as I said, we are not going to do the precise definition, but when we are having multivariable, it's harder to really prove it without the definition. But it is easy to see that if you have sort of two passes approaches the terminal point AB, as illustrated on this graph. So what it says was, when you are close, when the point is close enough to AB, all the outputs, all the values of the function will fall very close to L. But there are many ways you can get to AB inside this ball, right? As we illustrate here, you have many paths go toward the point AB. If you find two paths, okay, so say your f of x1 approaches, your xy approaches AB along path C1, so say this one is C1, and your xy also approaches AB from another path, say C2 is this. But when your independent variable pair goes toward the same point with different passes, your function actually are heading to different places. So f of x1, f goes to L1, a value, when you go along past C1, but it goes to another point, another value, when you go along past C2. Then, when they are going to meet at AB, they are not going to meet on the output side, the value side. Then we know that the function doesn't have a limit at this point. The limit does not exist at this point. Okay, so we will need a stronger statement to show, to find limit. But it's, in a way, it's easier to say there's no limit with easier like proof. Okay, if you can find two paths that go to the same point, but the value side don't agree, then the function doesn't have limit at that point. Okay, so first example, let's see. I'm not going to make you guess. We are going to show that the function x squared minus y squared over x squared plus y squared doesn't have a limit at 0, 0. So the function works this way. On the domain side, you are having two variables, you are in R2, and then you are going to map it to a single dimension value side, the number line. And we are looking at the point 0, 0, and there are many ways you can approach 0, 0. So say you go this way, you go this way, you go this way. But in particular, we are going to look at you approach the origin with x along x-axis or along y-axis. It doesn't really matter from above or from below. So I'm going to do both at the same time. Okay, so if xy approaches the origin along the x-axis, what happens is that, let me get another color. So you go this way. So pretty much your y remains 0. So y is 0 all the time, and x is moving toward 0. Then when that is the case, the limit of your xy approaches 0. Well, I shouldn't write this way because it's not really, we don't know if it exists yet. So when y equals 0, x approaches 0 with this x squared minus y squared over x squared plus y squared becomes y equals 0, x squared minus 0 over x squared plus 0. So that would be x squared over x squared. As x approaches 0, x is not 0. So x squared is not 0, x squared over x squared give you 1 anyway. So you are having 1. Now, if you are going to make xy approaches the origin along the y-axis, what happens will be when you go along y-axis, y is changing, but the x remains 0. So x remains 0 the whole time y goes to 0. If that is the case, you are making y moving. But in the function, actually x is 0. So it's 0 minus y squared and 0 plus y squared. And this, same thing, 0 doesn't really contribute in addition subtraction, and y won't be 0 until it gets 0. So you are having limit of y approaches 0, -1, which doesn't depend on y, so -1. Apparently, you are having two different limits along two different paths, so the limit x squared minus y squared, x squared plus y squared does not exist. Okay. These are the two paths I choose. I can choose other paths. Say I want to go to 0, 0 along x equals y. That means I'm getting there by this way. Well, it's pair. Again, I don't want to do from the positive side or the negative side because it will be the same. Okay, so your point get close to the origin from the diagonal way. If that is the case, you are going to have, x equals y, and when x goes to 0, y goes to 0 the same speed. You will have x squared minus y squared over x squared plus y squared, but x equals y, so, or y equals x, since I'm keeping x. So it's x squared minus x squared, and x squared plus x squared. This is 0. Okay, so what I'm trying to show you is that when you have two different limiting value, probably there are more, but as long as you pick two, you show that the limit does not exist. All the limit along different paths, when you are heading to the same point, will have to agree, like all end up with the same limit value. That's how a limit can exist. So as long as you find two things that aren't the same, does not exist. After defining limit, we can talk about continuity. A function f of two variables is called continuous at a point if the limit of the function heading to that point not only exists but also agree with the terminal value, same as first one variable functions. So if you know that along, here's your AB, and along all different passes, the value side will all go to the same point, then the limit exists. If that limit happen to be the value, then your function is continuous. And we say f is continuous on a domain if f is continuous at every point inside the domain. And several nodes. All polynomials are continuous on R2. So, because that's their domain. And the rational function is continuous on its domain, which means on each pieces except the zeros of the denominator. So, when you are having a rational function which is a quotient of polynomials, the denominator can't be 0, right? When denominator equals 0, it's not in the domain. So when you take those points away, the rest area, well, pretty much the rest part of the R2, the function is continuous. And actually it's true for other functions, but I'm not going to list all of them. I'm going to just say it once. If f and g are both continuous, then you can do compensation. Okay, so you can put all these functions together. If every step of the function is continuous, the whole thing is continuous. So for example, when you do e to x squared minus y squared, that is a continuous function at any point because this is a polynomial and e doesn't really have any E has domain also in R2 everywhere. So that means it's continuous everywhere. And in particular, when you are having continuity, you know the limit exists. And you actually know the value is the terminal and the value of the function. The third note, we don't have L'Hopital's rule when we are computing limit of multivariable functions because you don't know whether you are going to do the derivative with respect to x or y. Okay, so in short, we don't have L'Hopital's rule for multivariable functions. Finally, go back to the example that we did. Our function x squared minus y squared over x squared plus y squared was not continuous at 0, 0. Why was that? It's supposed to be continuous on its domain, right? But actually 0, 0, the origin makes denominator 0. So that will be 0 squared plus 0 squared, which is 0. 0 is the only point that is not in its domain. And for that reason, it's possible that it's not continuous. And actually, it's possible that the limit does not exist. And that is the reason it doesn't exist. Sometimes it still do. Like even if the point is not in the domain, you still can have a limit at that point. So not in domain doesn't guarantee you not continuity. Okay, but in domain guarantee you continuity. Next two examples, we are going to find the limit or show that the limit do not exist. So first example, we are looking at the same function x squared minus y squared over x squared plus y squared. And this time our xy approaches to 1. To 1 is in the domain. Of our rational function so you have the limit. You have, first of all, limit exists, and also the limit is the value would just be f of 2, 1, which is 2 squared minus 1 squared over 2 squared plus 1 squared, and that is 4 minus 1 and 4 plus 1, so we get 3 over 5. Okay, so we get it by continuity. Second, question B, I'm having the limit of x fourths minus y fourths over x squared plus y squared, and my xy approaches to 0, 0. So first notice that 0, 0 is not in the domain. It makes a 0 denominator. But if you look closer, you will see that actually the numerator can be factored. The numerator actually is x squared minus y squared, x squared plus y squared, difference of squares over x squared plus y squared. And as long as x squared plus y squared is not 0, which means x and y are not both 0, this means x, y are not both 0, then x squared plus y squared can't be 0, which means you can actually cancel them. But when we are looking at x, y approaches 0, 0, the only point that doesn't matter is the 0, 0 point, right? So when your x approach there, it's x, y approaches there, it's not the origin, which means you can cancel your x squared plus y squared from numerator and denominator, and that means you're having a polynomial and you can plug in your x squared and y squared, you still have 0. Okay, so here what I'm trying to show you is x squared plus y squared is 0 at the origin, which means the origin is not in the domain. Sometimes the limit does not exist. Sometimes the limit does exist. It's just not equal to f of 0, 0 because you can't plug in 0, 0 in the original function. Okay, in this case, actually it's called a removable singularity. But you don't have to worry about that. The point is the limit do exist. Even the function is not defined there. Okay, now you can pause the video and try practice number 1 and number 2. Next, we are going to talk about partial derivatives. When you have one variable, it's derivative. When you have two variables, you can't do the derivative at the same time. So you have to make one variable change at a time. That's why we have partial derivatives, which is sort of like I'm looking at when x changes, how the function change, or when y changes, how the function change. Okay, those are our derivatives, partial derivatives. So fx is the limit when we keep y the same, but we make x change. As h approaches 0, you do f of x plus h comma y minus f of xy over h. So throughout the thing, y does not change at all. It's just a fixed number. Similarly, you can make y move while x is the same number. Throughout this process, x is x, a value, but y, you make y value goes from y plus h to y, and h approaches 0, right? So the change is on y this time. The fy is the limit of f of fixed x, y plus h, minus f of xy over h. And for that reason, if you understand how the form or the definition of these partial derivatives work, you will understand why when we find fx, y is not moving, so y is just a constant, and we differentiate f of xy with respect to x. Y is a constant, y has nothing to do with x. Or the other way around, when you are looking for fy, x is a constant, and you differentiate the formula, the function with respect to y. Partial derivatives are pretty much the derivatives of functions, so of course they are useful, they are important, but also because of that, you have a lot of notations for the same thing. Okay, as you can see here, they all mean the same thing, the partial derivative. So fx, okay, f partial x, maybe you want to call it f partial x, or fx is, if you want to emphasize the differential form, it's not the little d anymore. Little d has a different meaning. You have to use partial to emphasize you have more than one variable moving at the same time. But now you are fixing all the other variables but only making x move. So it's a partial x. Or if you want to emphasize the function, you bring the function down on the side. In this way, the partial x becomes sort of like a operation on the function. Also, you can give the output f a particular variable z, then you will have partial z partial x. Okay, that's that. Then, since you are having two independent variables, x is the first slot, y is the second slot, instead of saying fx, you can also say f1. That's your first partial derivative. Or d1, this is like in the bigger derivative set, you are looking at the first coordinate-ish, or the x coordinate. Okay, so that's the d1 or dx f. For now, pretty much I will use, sort of these notations that actually we have been using all the time. The only thing is you can't just say f prime anymore, so you have to say fx or fy. Or, the f dx becomes partial f partial x. So, or, it used to be dy dx. Now, since it's not y anymore, it becomes, partial z partial x. So I think these four notations in the box are sort of like the regular ones that the similar ones that we have been using in one variable functions. And so we are going to sort of use them more, at least for now. Similarly, for the y set, you have the same thing. It's just that y is the second variable, so instead of f1, you are looking at f2. Okay. It might be scary at this moment, but when you are really computing them, it's very easy in the sense, instead of having to use chain rule every time you see a variable, when you are differentiating with respect to x, you can ignore y. They are constant. And when you are differentiate with respect to y, you can ignore x, right? So actually it's nicer than just consider y as a function of x. Anyways, let's see. My example 3, we are given a function f of x, y is 4 minus x squared minus 2y squared. And we are going to find fx of 1, 1 and fy of 1, 1. So I need to find the function to have the value. First, I need to know f partial x with the general form. And that would be, I differentiate this function with respect to x. 4 taking derivative 0, again with x, with respect to x. Minus x squared taking derivative with respect to x, 2x minus 2y squared. That's constant. So another 0, I'm ending up with negative 2x. So plugging in my 1, 1, it's actually negative 1 x, y times this one, okay? And that's negative 2. F partial y of x, y would be, going back to the formula, I'm taking derivative with respect to y. 4 is constant. X squared is also constant. Now y, I have 2, then 2y, so minus 4y. And again, I'm plugging in my 1, 1, and I'm taking this for my y. So negative 4 times 1, which is negative 4. Okay, so f partial x is negative 2 at 1, 1, and f partial y is negative 4 at 1, 1. What it means is, if you look at the two graphs I put here, you fix, remember what it means, you fix the other coordinate. So when x and y are both 1, if you plug in the function, you will see 4 minus 1 minus 2 equals 1. The z coordinate, the output is also 1. So you are on the curve, on the surface with the dot. The blue is like the surface, and then the pink is the dot of our 1, 1. And what these two functions are is like you sort of slice the surface open, the blue surface open along perpendicular to the y-axis, that is where y equals 1, or you slice it open with perpendicular to the x-axis at 1, which will be x equals 1, the plane, x equals 1. So you fix y. The first, you fixed y, and you look at when you slice it, you will get a curve. Okay, so I'm not sure if you can see it clearly, but there's a blue curve sort of here. That's like where this plane y equals 1 meets the surface. And then the negative 2 is the slope of that point, the tangent point of this, the slope of the tangent line at this point. Similarly, if you cut the surface open and with the plane x equals 1, you will see when you cut the surface up, you'll see a boundary, which is a curve, which is this one, the blue one, the sort of darker blue one. Okay, so this is the curve that you see on the surface at x equals 1. Then this is a function of y. The negative 4 you got is the slope of the tangent line with respect to y, of course, at 1, 1, 1. Okay, so that's what they are geometrically. But we are going to, I want to show you they are still slopes of a tangent line since they are derivatives, but, for now, I need you to know how to compute them. Similarly, we can extend our definition to more variables, say 3-variable function, f of x, y, z, equals x times sine y minus z. Then you will have three partial derivatives, fx, f partial y, and f partial z. F partial x will be, in this function, I'm differentiating with respect to x. Y and z are both constants or parameters, so sine y minus z also is parameter. I'm actually having a coefficient times x. When I take derivative, I just get the coefficient. So f partial x is actually sine y minus z. F partial y will be, well, my variable is here. So first of all, x is a coefficient. I will keep it. Then I'm differentiating sine y minus z. That will be cosine y minus z times the derivative of y minus z. And that will be x cosine y minus z times 1. So you get x cosine y minus z. See, finally, f partial z will be sort of the same thing. You are differentiating with respect to z. X is the coefficient and your z sits in sine. So you copy the coefficient, you take derivative on sine, you get cosine y minus z. Then you are doing the chain rule by passing the derivative on the y minus z part. And that will give you a minus 1. So the f partial z will be negative x cosine y minus z. That is the partial derivative. You have three variables, you have three first partial derivatives. First means you take derivative once. Okay, just like first derivative, second derivative, third derivative, f prime, f double prime, f triple prime of a single variable function. Not that x is the first, y is the second. Okay. Last example, but it's a long one. We're going to find partial z partial x and partial z partial y if z is defined implicitly as a function of x and y by the given equation. So in this equation, yes, you can solve for z, but we want to find the derivatives without solving for z. Okay, so if you want to find partial z partial x, what happens is x is the independent variable that you are differentiating with respect to, y is constant, and z is a function, which means you are going to do chain rule when you meet z. Then we differentiate the whole equation with respect to x. Let me copy the equation one more time. Differentiating term by term, x third, differentiating with respect to x, that's 3x squared. Y third, constant, differentiating 0. Z third, z is a function of x, so when you are differentiating z, you will have differentiate the derivative with respect to z times the derivative with respect to x, chain rule. Now, 6xyz, this is a little bit tricky. You actually want to read it as 6y x z, because y is a constant, 6 is a constant. So what you are really having is 6y times xz. This is a product rule with a coefficient 6y, where you differentiate the x with respect to x, you get 1 times z plus you have x times z prime equals derivative of 1, 0. Okay, now let's write it a little bit better, expand them in the sense of, non dz dx term, a non-partial z partial x term, and, partial z partial x term. So 3x squared plus 3z squared partial z partial x plus 6yz plus 6xy partial z partial x equals 0. And I am going to keep the partial z partial x term on my left. 3z squared plus 6xy partial z partial x. And I'm going to throw the other two terms on my right. 6yz. Then I divide by the coefficient. Equals negative 3x squared minus 6yz over 3z squared plus 6xy. They both numerator and denominator were all four terms that you'll see have a 3 in all of them. So I'm going to reduce it. Negative x squared minus 2yz over z squared plus 2xy. That's my partial z partial x. Similarly, I can do partial z partial y. I don't have room, so I do it over. With respect to y, you have x squared plus x third plus y third plus z third plus 6xyz equals 1. This is nice in the sense, y now x is constant. With respect to y. X is constant, z is function of y is the variable. So taking derivative, x third give you 0, y third give you 3y squared, z third give you 3z squared followed by dz partial z partial y. Then the yz is the product rule with the coefficient 6x. I'm having 1 times z plus y times derivative of z partial y equals derivative of 1, 0. So 3y squared plus 3z squared partial z partial y plus 6xz plus 6xy partial z partial y equals 0. And then I keep my 3z squared plus 6xy on my left. And I throw the other two terms without on my right. Then I'm having partial z partial y equals negative 3y squared minus 6xz over 3z squared plus 6xy. And reducing the 3. Negative y squared minus 2xz over z squared plus 2xy. That's my partial z partial y. Okay. So implicit differentiation. Well, very similar. I hope you still remember we were solving for dy dx given a function of x and y. So this is very similar, but you have just one more variable, one more sort of constant kind of variable. Okay, now you can finish the practice number 3 through number 5.